All right, good morning, everybody. Y'all doing okay? Y'all have any troubles with the screening test that I sent out on Friday? I didn't get that message.
I don't know if we had a mess. I never.
Okay, that's okay. We are gonna do the quick test problem, so you might feel a little bit behind. Let's go back. We're gonna do the problem in class. So if you didn't, you can probably sort of catch up to what we're gonna do. But I'm not gonna cover that very all directly. But we will cover it in the concept test and what have you. So some of it, if you're in lab, you might have picked up already in lab, and then we'll do multi-loop circuits. But, well, we're going to start here on page 152 and just go back and do some of the quick tests that were embedded within those pages, dealing with combination circuits, and then we'll move on to multi-loop circuits. All right, so let's go ahead and start with this following circuit. We'll use this for the next several questions. What is the equivalent resistance of this circuit? So when you do this, you want to do similar to what you did with capacitor circuit. Start with the only part that is, or start with the parts that are only series or only parallel. Combine them, find the equivalent of that, and then go outward from there. Remember, your equivalent resistances add up differently than equivalent capacitors. You switch, right? So resistors in series, you add up. Resistors in parallel, you do the inverse of the inverses. If you didn't get your exam, just see me afterwards. Brett, I have your exam. Just see me afterwards. Yeah. Oh, it's on page 152. If you finish this one, go on to the next one. Do about 10 more seconds. Stopping at 135. Just guess if you're not sure. Okay, let's see. So I combine my 1 and my 1. That becomes 2 ohms. Just 1 plus 1 is 2. And then my 2 and my 2, that's a 1 over a half plus a half, which is also 1. So that becomes 1. And then I have a 1 and a 1 right here. So that's 2 ohms. And so I'm left with two 2 ohm resistors in parallel. And so it's going to be 1 ohm. So A is the right answer. Let's try the next one. What is the potential across R3? Is it 12, 6, 4, 3, or is it 5.4? Start the clicker and put in your answer if you have it. It's the potential across this resistor right here. Alright, about five more seconds. I'll go to 38. 38. Okay, so what was B? 6 volts. B is right. So on this, I have 2 parallel branches. I have this parallel branch up here, right here, and I know across that parallel branch I have 12 volts. It's as if those 2 resistors are hooked up individually or together with my 12 volt battery. And then likewise across this parallel branch I have 12 volts. And so if I just look at this bottom one, because that's where R3 is, I imagine I have a 1 ohm resistor and a 1 ohm resistor hooked up to my 12 volt battery, right? That's just drawing these two resistors are here because they add up to give us 1, and then the other 1 ohm resistor. And now I have two identical resistors, and so I can just say, well, this has to be 6 volts and this has to be 6 volts. Or I could say the current through here, I, is equal to V over R. That's equal to 12 volts over the equivalent resistance, which is 2 ohms, so that's 6 amps. So I have 6 amps here and 6 amps here, because resistors in series have the same current. Remember, go back to your original rules. Resistors in series have the same current, and V equals IR, so 6 times 1 is 6 volts. And then further, the 6 volts and the 6 volts here have to add up to equal the total voltage, which is 12 volts. All right, so if this resistor has 6 volts, then both of these resistors also have 6 volts, because resistors in parallel have the same what? Voltage. They have the same voltage, right? So I have 6 volts on both R3 and R4. Let's go to the next one. If R3 is removed, what happens to the current through R1? If R3 is removed, what happens to the current through R1? Go down, go up, or remain the same? All right, I'm going to stop at 30 seconds. 30 seconds. Ask your neighbor if you're not sure. All right, before I do that, I want to show you something. So I want to know if R3 is removed, what happens through R1, to the current through R1. Notice here that R3 is in this parallel branch, and R1 is in this parallel branch. So what you're asking yourself the question is, if I change the resistance down here, and how am I changing it? Well, if I remove this resistor, I increase the resistance of this branch. So I'm increasing the resistance of this branch by removing the resistor. Because remember, when you add resistors in parallel, the equivalent resistance goes down. I'm giving those electrons more paths to take. So if I increase the resistance of this parallel branch, how does it affect the resistance, or rather the current, through this branch? So if I remove R3, what happens to the current through R1? Does it decrease, increase, or remain the same? Change your answers if you'd like. Does anybody want to change their answers? Oh, okay. Give me just a second. I'm going to stop at 2 minutes. What is it about two parallel branches, y'all? How do they act with regards to one another? Two parallel branches. How do they act? If I change one, how does it change the other? It doesn't change the other. Parallel branches are entirely independent of one another. So if I change one parallel branch, the other parallel branch doesn't change at all. All right, I'm going to stop at 2:32. Okay, good. C is right. It remains the same. If I change one parallel branch, the other doesn't change at all. It remains entirely the same. Okay, which resistor has the least current traveling through it? R1, R3, or R5? Think about your current as it moves through that circuit. It's going to split up at the junctions. And so then where will it have the most current when it goes through, and how does it split up going through those junctions? Or rather, which one has the least current? R1, R3, or R5? Or do all the resistors have the same current? No, they all have the same current. All right, I'm going to stop at 45. B, R3, is that right? Yeah, that is right. So B is right. Let's go back. So R3 has the least current. We can think about the current coming off of here. In fact, we said it was 6 amps, right? If the equivalent up top is 2 ohms, then the total current is 12 divided by 2, V over R, which is 6 amps. So 6 amps coming up here. Part of it goes this way, part of it goes this way. And in fact, I know that this is 2 ohms. Remember what this bottom branch was? What was the bottom branch? No, it wasn't 1. Wait, this was 1. But when I add 1 and 1, it becomes 2. So this branch is also 2 ohms. So my 6 amps then is going to split here out. What will I get up top? What current will I get up top here? If I have 2 branches that are identical, not 6, I'm not going to get 6 amps. I'm going to get 3 amps. Remember that junction rule? The junction rule says that the current going in splits up into a sum that's equal to the total current. So if I have 6 amps going in here, I have 3 amps and 3 amps going in both of those. Now they don't have to split up evenly. I can get different currents going through the different branches, but because I have 2 ohms and 2 ohms here, then I'm going to get 3 amps and 3 amps. You also know this because I have 6 volts, as we said before, across this branch, and 6 volts here. If I have 2 ohms, I is V over R. 6 volts over 2 ohms is 3 amps. So I have 3 amps on both of those. So I get 3 amps here, 3 amps here. Here, my current splits again. What is my current through R3 then? It has to be 1.5. That 3 amps splits into 1.5 and 1.5, and then it comes back together here to give me 3 amps. So looking at R1, 3, and 5, R3 has the smallest current of those 3. It also has the same current as R4. All right? We'll see some other questions like that as well. Now listen, on the test, you're going to have a combination circuit, which will be something similar to this. And then you'll also have a multi-loop circuit, which you also saw on those screen cams, but we'll work through some multi-loop circuits. So 2 different kinds of circuits that you'll see on the coming test, just after spring break. Okay. Let's go. There's the Kirchhoff's rule and the loop rule. Listen, if you haven't gone and done this, make sure that you do. We'll use them, but I'm not going to go over them here. Likewise, these rules about finding the direction and the sign of the potential is quite important. Again, we'll use these rules, so if you haven't looked at this yet, then you should go back and take a look at it. All right, so let's try this quick test. What is the current in this circuit? And here we're going to use our loop rule. Remember the loop rule which says the sum of all potentials in a closed loop is equal to 0. So what you want to do here is pick a direction for the current. Pick any old direction for the current. Pick any old direction to travel through the circuit. Let me get you started because I think maybe some of you haven't watched the videos. Am I right? Not bad. Okay, well, let me get you started on this. And then we'll work through some examples. You should go back and watch those too, because I'm not going to cover that here. But first thing you want to do is just pick a direction for the current. Any old direction, doesn't matter. I'm going to say that the current flows in this direction. Doesn't matter what direction I pick. It could be wrong or it could be correct. And then you want to pick a direction to travel through the circuit. Say I'm going to go in this direction through the circuit. And then you want to go through and ask yourself on each element, what is the sign? Okay, I'm getting it. What is the sign of the potential? As I move through the circuit, what is the sign of the potential? So, is the potential here positive or negative? as I'm going in this direction. I'm going with the current. Does the resistor have a positive or a negative potential drop or rise? It's negative. When I go with the current, I get a potential that's negative IR. Here, as I'm going from low to high, do I experience a drop or a rise in potential? That would be negative V or positive V. I get a positive change in potential. My electrons gain energy when I go in this direction. Here, going with the current, negative IR. Here, positive, negative 18 volts for my electrons. Negative 18. Going from the big side to the little side, I get a negative change in potential. And here, I get negative IR. So you want to write the loop rule for this. The sum of the potentials equals 0. I get negative IR plus 12, negative IR minus 18, negative IR. All of those have the same current because there are no junctions, so the current doesn't split up. So what is that current? Go ahead and try to figure out that current. Alright. About 15 or 20 more seconds. Stop at 410. 410. Just in case if you're not sure. Okay, let's see. We're sort of all over the board here. But I'm going to write out the loop rule. As I move from this point in this direction, I get negative 1 times I. That's R times I. Negative 1 ohm times I. Plus 12. Minus 2 times I. Minus 18. Minus 6.6 times I. That's all equal to 0, and then I solve that for I. So I get negative 1, negative 3, minus 9.6 I, minus 6 equals 0. And so I is 6 over negative 9.6. So that must be 0.63. It actually comes out negative. Now what that means is if it comes out negative, that means that when I chose the direction for the current right here, that I chose it incorrectly, that the current actually goes the other way. And if you look at this, you can probably tell that that's the case, because this circuit is fairly simple. It's not a multi-loop circuit, it's just a single loop circuit, but with multiple batteries. Notice this battery is pushing a current in this direction with 18 joules per coulomb, the amount of energy that it gives. This is pushing a current in this direction, the opposing direction, and so this guy is going to win out and push the current in this direction because it's giving the electrons more energy. All right, so we could have reasoned what the current was, the direction of the current there, but when we get to multi-loop circuits, you won't really be able to reason. You won't be able to see what the direction of the current is. All right, let's try a few clicker questions from the back. And you should have done this example. It was in the screencast, and but we'll work. This was just with variables. We'll work one later with just with numbers. So let's try these. Have we done any of these yet? Chapter 4? No. All right, let's do some of these. We'll see some more combination circuits. Okay, so here I have a 9-volt battery with 3 resistors that are identical. What is the potential across each resistor? I'll stop at 38. 38. Okay, awesome. C is right, 3 volts. Because I have identical resistors, they split that voltage evenly. In the circuit below, what is the voltage across R1? Remember, a couple different ways you can do this. You can think about how the voltages are distributed across these 2 different resistors, or you can find the equivalent resistance, 6 ohms, find the total current, and then find the voltage across each individual resistor. V is equal to that current times the resistance. Remember with resistors too, the bigger resistor has the bigger voltage. That was unlike capacitors where the bigger capacitor had a smaller voltage. We're going to stop at 105. 105. Okay, good. 8 volts is right. I'm going to have 8 volts across the 4 ohm resistor and 4 volts across here. My equivalent is 6 ohms. I have, 6 ohms, so I have 2 amps coming through the circuit. 2 times 4 is 8. 2 times 2 is 4. 8 volts, 4 volts, 8 plus 4 equals 12. So I'll have 8 volts on the bigger resistor, 4 volts on the smaller resistor. The resistor is smaller by a factor of 2. The voltage is also smaller by a factor of 2. What is the current through R1? Remember, resistors in parallel act independently of one another, and it's as if each resistor is hooked up individually to the battery. I'll stop at 43. 43. Just guess if you're not sure. Okay, D is right. I have 10 volts across both of these resistors. I have 10 volts here. I have 10 volts here. I'm looking for the current through here. I is V over R. That's 10 over 5, which is 2 amps. So D is the right answer for that one. Point P and Q are connected to a battery at fixed voltage. If you add resistors to the parallel circuit, what happens to the total current? Now the total current is the current coming through these points, through this part of the circuit. So as I add resistors, what happens to the total current in this circuit? I'll stop at 40 seconds. 40? Just guess if you're not sure. Okay, so it looks like you're putting either A or B. It is one of those. It's either increases or remains the same. What I'm asking for here is the total current through the circuit, the current that comes up through here. Now what I know about resistors in parallel is that resistors in parallel all have the same voltage. So if I have 10 volts here, I have 10 volts here, 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 and here. So I've already said, actually, we had a question before where if I add a resistor here, or take away a resistor, then the other resistors are unaffected. All right, so if these resistors are unaffected, as I add more and more resistors, what's going to happen to the total current coming up through here? Think too about the junction rule, and what the junction rule says about ingoing and outgoing currents, incoming and outgoing currents. That, remember the junction rule said that the current incoming is equal to the sum of the outgoing currents. I'm going to stop at 105. 105. Why don't you ask your neighbor what they put? Ask your neighbor what they put. And if you're different, then tell them you're correct and they're wrong, whatever. Everybody ask your neighbor what you put? Don't ask one another. And you put the same thing, okay. Okay, a little bit better. I'm going to stop at 135. Okay, B is, oh, no, B is not the right answer. Oh, we went the wrong way. Huh? It increases. It doesn't affect that on the side. Right. So look, if I have, say, 2 amps through this resistor, they're all the same. Let's say it's a 10-volt battery, 5 ohm resistor, so I get 2 amps on all of these. If I add another resistor here, I go from having 8 amps to having 10 amps. So as I add more and more resistors, I add more and more current to my total current. So if I just have these 4 resistors, I have 8 amps. But then if I add another resistor, I also add another 2 amps. You can think about it too. Remember the equivalent resistance of resistors in parallel? If I add resistors in parallel, what happens to the equivalent resistance? Does it go up or down? It goes down, right? I'm giving those electrons more paths to travel through. So if the equivalent resistance goes down, that means the current goes up. V is IR. If R goes down, I goes up. So that's true here too. As I add resistors in parallel, the total current goes up. We'll see that this is true for our household circuits too, which are laid out in parallel. And so if you have a household circuit and you keep adding more and more resistors, adding more and more devices to your circuit, then eventually you're going to reach a current here that is too big. And it's either going to burn your house down or kick off your circuit breaker. Hopefully the latter, not the former. We'll see that in a bit. Okay, so here current flows through a light bulb. If a wire is now connected across the bulb, what happens? So I have a light bulb, then I take a piece of wire and I connect it across the bulb. All right. So before I just have a light bulb, and then I add that wire connecting one point before the bulb to one point after the bulb. Are y'all doing this on purpose? Seriously? No, it's okay. So when I have current that comes to a parallel branch, remember we said that current will take that path of least what? Least resistance. Okay, so if I have a current, an electron that comes up to a branch in a circuit, it's going to say, do I want to go this way or do I want to go this way? And the way it will decide which way it goes is which the easiest way, which is the path of least resistance, as I said. So that electron is going to take the path of least resistance. And then more electrons will come along, and more will take that path of least resistance, dependent upon what is the proportions to the resistances. So here, an electron coming along here will come to this point, and it's going to say, what's the easiest way to go? And the easiest way to go is the way that's going to go. Okay? So let's look better. I'll stop at 155. Okay, C is the right answer. But a lot of you had that half the current flow. So if you put that, that's okay. I mean, you're in good company. But it's not correct. The current here doesn't split evenly. The current splits in proportion to the resistances. So if I have a small resistance up here, I'm going to get a lot more current flowing through this branch than through this branch. So C, I did mark C, right? Yeah. And in actuality, in reality, the wire does have some resistance. It's a very, very small amount, but we're assuming that it has basically no resistance compared to that of the light bulb. All right, two light bulbs, A and B, are connected in series to a constant voltage source. When a wire is connected across bulb B, what will happen to bulb A? Now, if I connect that wire across bulb B, that's effectively taking bulb B out of the circuit, because all my electrons are going to come through here, and none are going to go this route. They're all going to go this route when I close this switch. So what's going to happen to bulb A? Will bulb A grow brighter, the same, dimmer? Will it go out completely? Or explode? Okay, doing well. I'll stop at 45. 45. Okay, good. Bulb A will burn brighter than before. Imagine if I had 12 volts here. If bulb A and bulb B are both going, I'll have 6 volts. But if I take out bulb B, now I no longer have 6 volts. I have twice the energy going to bulb A. I have 12 volts of energy per charge going to bulb A. Bulb B, of course, just goes out. All right, two light bulbs are identical, the same resistance R. So that means I have a resistance R here, R here, R here, and here. Which circuit produces more light? And consequently, which circuit uses more power? Because brightness is the same as power. When I talk about the brightness of something, I'm talking about the power. Okay, doing well so far. Go ahead and put in your answer. I'll stop at 42. Okay, awesome. A is right. Imagine if I have 12 volts on these batteries. That means I have 12 volts here, 12 volts here. But I have 6 volts here and 6 volts here. So we have some expressions for power, and one of those expressions is V squared over R. That was in your screencast. I'm pretty sure we didn't get this. Oh no, that was last chapter actually. That was chapter 3. But one of our expressions is this. If R remains the same, and I change V, then I'm going to change the power. So these bulbs will be 4 times as bright as these bulbs. So you get a lot more power out of that parallel circuit. Hey, what happens when you divide the circumference of a pumpkin by its diameter? You get pumpkin pie. Hey, it's pie day, right? It's March 14th. And there is a pie throwing dealie at noon. Do y'all know where it's going to be? NCSS folks? It'll be around here, probably out in the little courtyard. I think they're going to have Drs. Cortez, Lowe, and Wayman? No, Marlowe. Marlowe, I'm pretty sure. They've been raising monies to do outreach with local schools, but so you can drop by at noon and see who they're going to get. I'm thinking Dr. Lowe. Yes. Yeah, that would be the best. Okay. He's not goofy.
Yes, he is.
I like him.
I do too.
I do too. Yeah. Who doesn't like him, right? So 3 light bulbs. If you don't say anything, but I think most people do like him. Actually. 3 light bulbs all have the same resistance of 1 ohm. By how much is the brightness of bulb B greater than the brightness of bulb A? Answered this just last slide if you were listening. But how much brighter is bulb A? Or excuse me. By how much brighter is bulb B greater or smaller than the brightness of bulb A? Is B twice as bright as A? the same, half, quarter, or 4 times as much. Let me remind you the power. If I'm holding my resistance constant, power is equal to V squared over R. If R is constant, power has this expression of V squared over R. So by how much brighter, greater or smaller, is B compared to A? All right, I'll stop at 120. Good. That's some last minute rallying. Our voltages are different by a factor of 2. So bulb B has half the voltage. If it has half the voltage, that means it has 1/4 of the power. So half the voltage gives me 1/4 of the power, so it's 1/4 as bright as bulb A. What happens to the voltage across R1 when the switch is closed? Close this switch here, add it R2. What happens to the voltage there? Think about what happens to the equivalent resistance of this thing. Does it go up or down? If it goes up or down, what happens to the voltage across this thing? Does it go up or down? And then what happens as a result to the voltage across R1? Here, let me step you through this. If I close this switch, what happens to the equivalent here? Go up or down of these two parallel. I'm adding a resistor, so the equivalent resistance gets smaller. So I can think about this as R1 and then R23. This has decreased in equivalent resistance by adding R2. That means that the voltage across this resistor has gone up or down by adding resistor 2. If my resistance goes down, what happens to my voltage? It also goes down. So now I'm asking what happens to the voltage across R1? Does it increase, decrease, or stay the same? I'll stop at 142. Okay, good. A is the right answer. But y'all were sort of all spread out before, with a lot of you actually putting decrease. The equivalent here decreases. That means the overall voltage here decreases. But since the voltages have to add up to equal the total voltage, if this voltage goes down, this voltage has to increase, has to go up. So V1 increases. What happens to the voltage across R4 when the switch is closed? So I close the switch, add in R2. What happens to the voltage there? This is a little tricky. Think about what happens to the voltages in the circuit. If I close this switch, adding R2, what happens to this voltage? Okay, doing pretty well. A good portion of you have the right answer. I'm going to stop at 42. 42? Okay, it decreases. So the equivalent resistance of this whole thing goes down. The equivalent resistance goes down when I add that resistor. That means the voltage also goes down in a similar way as we had before. So B is the right answer. And which resistor has the greatest current going through it? We had one very similar to this before. Think about all these resistors are the same. Think about how your current splits up. Which has the greatest current going through it? R1, R1 and 2, R3 and 4, R5 are all the same. Think about your current, how it splits up. Say we have 10 amps or whatever. We come here, it splits. It's going to split evenly, right? And then over here it splits again. It's not going to split evenly over here because I have different resistances in the two branches. I'm going to stop at 110. I'll go to 115. Okay, R5 is right. It has the greatest current. Imagine I have 12 amps coming off of here. That means I'm going to have 6 amps and 6 amps. And then up here in R5, what is my current going to be through R5? In R5, I have half the resistance of R3 and R4. Any idea what my current will be? The smaller resistance will give me a bigger current. It's smaller by a factor of 2, so I'm going to get what current through R5, do you think? No, I'm going to get 8 amps and 4 amps here. I'm going to get a bigger current down through this bottom resistor because I have a smaller resistance. A resistance smaller by the factor of 2, so I'll get a bigger current. So R5 is the bigger current. Okay, what is the current through branch P? 2, 3, 5, 6, or 10. Branch P is right here. All right, I'll stop at 35. 35. Says the junction rule says that the incoming currents equals the outgoing currents. Okay, good. D is right. I have to have 6 amps. Because I have 8 amps coming into this junction, I have 2 amps going out, so I also have to have 6 amps going out as well. That's just conservation of charge. You can't lose charges. But we're going to skip this one. We're going to do this one. You should know how to do this. We're not having a real banner day today. That's okay. But we want to find out which of these is the correct use of the loop rule for this multi-loop circuit. Let me help you step through it a little bit, okay? So here, I look at all these different equations that are written from the loop rule. Let's take this first one. It's written such that I have positive 2 volts, right? It should be positive from going from small to big, so positive 2 volts, minus I1. Oh shoot, that's that. Oh no, we're looking for the correct. Minus I1, so that's correct so far, minus 2I2. It would be minus 2I2 because I'm going with the current, but notice that this 4-volt battery is left out. If I wanted to make that first equation correct, what would I put in for this 4-volt battery? Plus or minus 4 volts? I would put in minus because I'm going from big to low, from high to low potential, and so that causes a drop in potential. So I know it's not A. Go through those other 4 equations and ask yourself the question, is this a correct or incorrect? And we're looking for the correct equation for this circuit. All right, doing pretty well. I'm going to stop at 210. 210. All right, good. Yeah, C is right. Let's look at C. We're looking for the correct answer. 2, we're looking at this one. I have 2 plus 2 minus 1I1. I know it's I1 because I1 moves through this branch of the circuit. Minus 4, so it's right there, minus 2I2. So that is the correct answer. It's very much like A, except it has the minus 4. All right. Let's, what time we have? We're going to start on this next one. We have 5 minutes left, so let's start on the next one, the next multi-loop circuit. But listen, you really need to go through, make sure especially you go through on the screencast that I sent out earlier. I think it was like link 38 or something on that website, and watch the part about doing this multi-loop circuit. But let's go on, and we're going to do this one. It's similar, but it just has numbers. So I want to know the current through each of these resistors. You shall have a problem like this in the test, a multi-loop circuit that you'll need to work out. Once you do it a couple times, I don't think it's that hard. So just spend a little time practicing it. There's one in your homework. You will have to work through one of these. You will have to solve a system of 3 equations. So I want to know the current through each of these resistors. The first thing that you want to do is label your currents. And so here, I'm going to label this current as I1, and I'm going to recognize that I1 goes through this part of the circuit. I'll label this current as I2. I'm going to recognize that I2 goes through that circuit. And then I'll label this current as I3. And I'm going to put it in that direction. So what I've done is I've chosen directions for my currents. I don't know if they're the correct directions. They may or may not be. You might be able to reason out what it is, but probably not. It's going to be kind of difficult as your multi-loop circuits get more and more complicated to figure out the direction of your currents. But it doesn't matter. You just pick a direction. Don't give much thought to it. Just pick it randomly. So I pick a direction for each of those currents, and then I write my 3 equations for the loop rule. I have 3 loops. I have the upper loop, I have the lower loop, and then I have the big loop. And we can write the loop rule for each of those. So for this one, let's write it for the upper loop first. I'm just going to pick a direction to move through the circuit. So I have to pick 2 directions. I have to pick the direction for the current, and I have to pick a direction to move through the circuit. I'm going to start right here, and I'm going to go in this direction. This is independent of your current direction. This is just, I'm going to go through the loop in this direction. And so for my upper loop, I get positive 6 because I'm going from big to little, from low to high, minus 1I2 plus 4 minus 2I1. That's equal to 0. That's from the loop rule. 6 minus 1I2 plus 4. Yeah, that's right. Then I'm going to do the lower loop. I'm going to start here and go in this direction, come through and do the lower loop. So the first part looks the same. And then in the bottom part, I get minus 2. And then that's it, equal to 0. Remember, it's minus 2 when I move from high potential to low potential, from big to little. My electrons are actually losing energy in that case. And then I'll do the big loop. Actually, I'm not going to do the big loop because we don't need to do it here. We only need 3 equations to solve this, and so I'm just going to write the junction rule. And so for the junction rule, I'm just going to pick a junction. There are only 2 junctions, so it doesn't really matter which one I pick. I'm going to say the incoming current equals the outgoing current. Now for this junction, I have 2 incoming currents. What are they? Right, so I have I1 plus I3. And that's equal to I2. So these are my 3 equations, And I want to solve these three equations to calculate then what is I1, I2, and I3. This is a pretty simple system of three equations. The one in your homework is a little more complicated. It requires a little more substitution. But this one's simple largely because there's no resistor in the bottom loop. All right, and because there's no resistor in the bottom loop, I can solve this equation directly for I2. And I find that I2 is equal to 4 amps. Comes out positive, so I know that I chose the direction correctly. Then I can solve equation 1, because now that I know I2, I can solve this for I1. And that's equal to 4 minus 10 divided by negative 2, which is 3 amps. So I have I2. Now I have I1, and then if I want to know I3, I solve the junction rule. So I do I1, which is 3 amps, plus I3 equals I2, which is 4 amps. And so I3 has to equal 1 amp. So now I've found all three currents, and then that's it. So on the test, you'll have to solve that, and just solve a system of three equations. It looks simple there, but you have to be able to get your equations set up correctly, and we'll work on that next time. And then also next time, I don't know if you remember, but last semester we solved the system of three equations by Gaussian elimination. You'll be able to get extra credit on the test. So if you know how to do that, that'll be a nice 5 points whatever you pick up. Okay? Go back and look at those tests if you haven't already, okay? And then we'll do more multiple choice next time. You have a great day.